August 19, 1942, Dieppe, France. Nearly 4,000 Allied troops lay dead or captured on the beaches. The lesson was written in blood. Capturing a defended port is suicide, but without a deep-water harbor, the Allied planners faced a death sentence of mathematics. Any invasion of France would need 12,000 tons of supplies every single day. Normandy had no port. Cherbourg was 60 miles away, and German engineers would blow it to rubble the moment the Allies came ashore. Winston Churchill scribbled 5 words on a memo to his chief of operations: "Piers for use on beaches." His staff thought he'd lost his mind. Build a harbor? From scratch? Float it across 80 miles of open ocean, then sink it on a beach that swings 22 vertical feet with every tide and gets hammered by 40-knot Atlantic storms? 11 months later, 50,000 workers across Britain were pouring concrete caissons 6 stories tall, welding 10 miles of floating steel roadways, and assembling the pieces of 2 artificial harbors, each one larger than Dover. Nobody told them what they were building. And nobody told the Germans it was coming. How do you deliver an invasion when there's nowhere to unload? You build the impossible, and you tow it across the sea. If you want more stories like this where the engineering saved as many lives as the soldiers, hit that subscribe button. And drop a comment below. Where are you watching from? I love seeing how far these untold stories travel. The conference room at Norfolk House in London's St. James Square held 27 men on the morning of August 24, 1942, but only one problem. Lieutenant General Frederick Morgan, newly appointed Chief of Staff to the Supreme Allied Commander, stood at the head of the table with a map of the French coast spread before him and a single question burning through every calculation. How do you invade a continent when you cannot capture a port? 5 days earlier, the beaches at Dieppe had turned into an abattoir. Canadian troops stormed ashore at dawn expecting to seize the harbor intact. German machine guns firing from concrete bunkers cut them down in windows of fire so precise that bodies stacked 3 deep at the waterline. Of the 6,086 men who landed, 3,623 were killed, wounded, or captured in 9 hours. The Royal Navy lost 33 landing craft and a destroyer. The lesson was absolute and unforgiving. Fortified ports cannot be taken by frontal assault, not without losses that would cripple an invasion before it began. Morgan's planning staff, codenamed Cossack, had spent 3 months analyzing every harbor from Brest to Calais. Cherbourg was the obvious choice, a deep-water port capable of handling the tonnage an Allied army would require. But Cherbourg sat at the tip of the Cotentin Peninsula, 60 miles from the proposed Normandy landing beaches, and German engineers had already wired every dock, crane, and warehouse with demolition charges. Intelligence estimates gave the Germans 3 hours to reduce Cherbourg to rubble. Even if the Allies captured it on D-Day, it would take months to rebuild. The mathematics were brutal and inescapable. An Allied invasion force would land 150,000 men in the first 48 hours, with thousands more arriving daily. Each division consumed 600 to 700 tons of supplies per day. Ammunition, fuel, food, medical supplies, spare parts, bridging equipment, artillery shells, tank tracks, radio batteries, everything an army needs to fight and move and survive had to flow across the beaches in a torrent that never stopped. By the 3rd week, the minimum daily requirement would reach 12,000 tons. By August, if the advance continued as planned, the figure would climb to 26,000 tons per day. Without a harbor, there was no invasion. And without an invasion, there was no second front, no relief for the Soviets bleeding the Wehrmacht white on the Eastern Front, and no end to the war before 1946 or 1947, if ever. Morgan leaned over the map, tracing the Normandy coastline with one finger. 50 miles of gently curving beaches, backed by farmland and small villages, with no harbor larger than a fishing port. The tide swung 22 vertical feet twice daily, among the highest in Europe. Atlantic storms rolled in with 40-knot winds and seas that could flip a landing craft like a toy, and the beaches themselves were open to the northwest, fully exposed to the prevailing weather. It was, by every measure of naval logistics, the worst possible place to land an army. which was precisely why the Germans had fortified Calais and left Normandy lightly defended. They knew what Morgan knew. You cannot supply an invasion over open beaches. Not for weeks. Not for months. Not at the scale required to break through the Atlantic Wall and drive inland to Germany. On August 30th, 1942, Winston Churchill sent a memorandum to Lord Louis Mountbatten, Chief of Combined Operations. The note was 3 sentences long and written in Churchill's characteristic scrawl. They must float up and down with the tide. The anchor problem must be mastered. Let me have the best solution worked out. Don't argue the matter. The difficulties will argue for themselves. Attached to the memo was a single phrase underlined twice. Piers for use on beaches. Mountbatten read it twice, then summoned Brigadier Bruce White, the 47-year-old civil engineer who had designed the port facilities for the British Expeditionary Force in France in 1940. White arrived expecting to discuss landing craft modifications. Instead, Mountbatten slid Churchill's note across the desk and asked a question that sounded like science fiction. Could you build a floating harbor large enough to handle ocean-going ships and tow it across the English Channel? White did not laugh. He did not dismiss the idea as fantasy. He went back to his office, spread out tide tables and weather charts, and started calculating. The English Channel between Portsmouth and Normandy was 80 nautical miles. A harbor capable of unloading 7,000 tons per day would require at minimum a dozen deep-water berths, protected by breakwaters long enough to dampen Atlantic swells, connected to the beach by piers that could rise and fall with the 22-foot tidal range. The structure would have to survive storms, resist enemy air and naval attack, and remain operational for months until the Allies captured and repaired a permanent port. White sketched the first design on September 3, 1942. Massive concrete caissons, hollow and buoyant, would be towed to France and sunk in an arc to form an artificial breakwater. Floating steel roadways mounted on pontoons would rise and fall with the tide, connecting the caissons to the beach. Pierheads anchored to the seabed would provide berthing for coasters, tankers, and LSTs. Old ships, obsolete freighters, and superannuated warships would be scuttled in a second line to provide additional wave protection. On paper, it looked plausible. In practice, it would require building 2 of the largest movable structures in human history in secret in less than 2 years and delivering them across 80 miles of submarine-infested water to a beach under fire. By July 1943, Cossack had approved the concept. The operation was codenamed Mulberry. 2 artificial harbors would be constructed in Britain and installed off the Normandy coast beginning on D+1. Mulberry A would serve the American forces at Omaha Beach. Mulberry B would support the British and Canadian sectors at Arromanches. Each harbor would be approximately 5 miles in total length with a target capacity of 7,000 tons per day, expandable to 12,000 if the invasion schedule held. The engineering requirements were staggering. 146 Phoenix caissons, each weighing between 2,000 and 6,000 tons, had to be cast in concrete, floated, and towed across the channel. 10 miles of flexible steel roadway mounted on pontoons called whales had to be fabricated and assembled. 93 massive steel floats, designated bombardons, would form an outer breakwater. 23 pierheads would provide berthing, and 70 block ships, stripped of guns and machinery, would be sunk as the inner wave barrier. The deadline was June 1, 1944. 11 months. The skeptics said it could not be done. Churchill said it must be done. And 50,000 workers across Britain, in shipyards and quarries and factories that had never built anything like this, began pouring concrete and cutting steel for a harbor that had to float, had to survive the crossing, and had to work the first time because there would be no second chance. The first Phoenix caisson took shape in a dry dock at Southampton in August 1943, and the workers who poured the concrete forms thought they were building a section of submarine pen or coastal defense. The security classification was absolute. Contractors received blueprints for individual components with no indication of final assembly. Welders joined steel plates without knowing whether they were fabricating pontoons or barge sections. Concrete crews poured foundations in timber molds 60 feet wide and 50 feet tall, working 3 shifts around the clock, and were told only that the structures had to be watertight and capable of floating. The Phoenix units were hollow rectangular boxes, reinforced with internal steel cross-bracing, divided into watertight compartments that could be flooded or pumped individually to control buoyancy. The smallest weighed 2,000 tons. The largest, designated Phoenix Type B, measured 204 feet long, 56 feet wide, and 60 feet high, displacing 6,4 tons when fully ballasted. Each unit required 2,500 cubic yards of concrete, 350 tons of steel reinforcement, and 6 weeks to cure before it could be floated out of the dry dock. By October 1943, construction was underway at 17 sites from Scotland to the Isle of Wight. Dry docks that had built battleships now cast concrete monoliths that dwarfed destroyers. The scale defied comprehension. In the Firth of Clyde, workers at the Ardine Point construction basin poured caissons in open water, building cofferdams to hold back the sea while concrete set. At Marchwood near Southampton, entire river estuaries were dredged to create assembly lagoons where finished Phoenix units could be sunk in shallow water and hidden beneath the surface until D-Day. The Mulberry project consumed more steel than the construction of 2 aircraft carriers and more concrete than the building of a major highway. The Ministry of Supply requisitioned every heavy-lift crane in southern England. Railway sidings were extended into shipyards to carry aggregate and cement. Timber for the formwork came from demolished buildings and salvaged dock pilings, every plank accounted for and recycled because there was no surplus anywhere in wartime Britain. Workers labored through the winter of 1943, the coldest in a decade, pouring concrete in freezing rain, wrapping freshly cast sections in tarpaulins, and heating them with coal fires to prevent cracking. One engineer remembered standing in a dry dock at dawn, watching steam rise from curing concrete, and realizing he was looking at something that had no precedent in engineering history. Not a ship, not a building. Something that had to function as both simultaneously in the worst imaginable conditions. The floating roadways, codenamed Whale, were fabricated in factories across the Midlands. Each section was 80 feet long, welded from steel plate and mounted on cylindrical steel pontoons called beetles. The roadway surface was wide enough for 2 trucks to pass, with raised curbs and tie-down points for securing cargo. The pontoons were designed to telescope vertically on steel piles driven into the seabed, allowing the roadway to rise and fall with the 22-foot tidal swing without losing structural integrity. The tolerances were measured in fractions of an inch. Too loose, and the roadway would jam or tear free in heavy seas. Too tight, and corrosion or impact damage would seize the mechanism. Engineers tested prototypes in a wave tank at the National Physical Laboratory, subjecting sections to simulated storm conditions for 72 hours straight. They measured stress, fatigue, and failure points, then redesigned the joints and ran the tests again. By January 1944, production was running at maximum capacity. Steel mills in Sheffield and Birmingham rolled plate around the clock. Welding crews, many of them women trained in aircraft production, joined sections in unheated warehouses, working by floodlight through winter nights. The sections were loaded onto rail cars, transported to coastal assembly points, and rafted together in estuaries where they floated low and gray, looking like nothing so much as segmented steel snakes coiled in the water. The bombardons were the outer defense, massive cruciform steel floats 200 feet long and 25 feet in diameter, anchored a mile offshore to break the force of Atlantic swells before they reached the Phoenix breakwater. Each bombardon weighed 350 tons and rode low in the water, designed to pivot and yield to wave action rather than resist it. The concept was counterintuitive. Instead of building a rigid barrier, the engineers created a flexible one that absorbed energy through controlled movement. 93 bombardons were fabricated at the Clyde shipyards, welded from riveted steel plate salvaged from decommissioned merchant ships. The work was brutal and dangerous. Riveters balanced on narrow catwalks 30 feet above the water, driving red-hot rivets through quarter-inch plate in wind that could gust to 40 knots. One welder was killed when a chain hoist failed and a steel section weighing 3 tons crushed him against a bulkhead. The accident was not reported in the newspapers. Security forbade any mention of the Mulberry project, even in casualty reports. His family was told he died in a shipyard accident. The details remained classified until 1947. By April 1944, the components were complete. 146 Phoenix caissons lay submerged in lagoons and river estuaries, their tops barely visible at low tide. 10 miles of whale roadway sat folded in sections at assembly points along the coast. 23 massive pierheads, each weighing 1,000 tons and equipped with bollards, fenders, and mooring gear, waited in Southampton water. The bombardons floated in the Clyde, painted gray and camouflaged with netting. And 70 block ships, obsolete freighters, and worn-out warships, stripped of armament and machinery, were anchored in the Thames estuary, ready to be scuttled on command. The Royal Navy had requisitioned 132 ocean-going tugs, the largest concentration of towing vessels ever assembled. Crews were briefed on towing procedures but not told what they would be towing or where they would be going. Captains received sealed orders marked to be opened only on receipt of code word Mulberry. The Ta. Security held. German reconnaissance aircraft photographed British ports throughout the spring of 1944, but Luftwaffe intelligence analysts saw only the usual concentration of landing craft and supply ships. The caissons were invisible beneath the water. The roadway sections looked like barge traffic. The bombardons were dismissed as floating breakwaters for coastal convoys. No German officer suspected that the British were building 2 harbors the size of Dover and preparing to tow them across the English Channel. On the evening of June 5, 1944, as the first wave of American paratroopers boarded their C-47 transports for the flight to Normandy, the tugs received the signal. Mulberry execute. Dawn +1. Crews scrambled to cast off, engines rumbling to life in the darkness. The tow cables, each 2 inches in diameter and rated to 200 tons of tension, were shackled to the bow eyes of sunken Phoenix caissons. Compressed air roared into the ballast chambers, forcing out seawater, and the massive concrete boxes broke the surface like breaching whales, water cascading from their sides. One by one they rose, riding low and sluggish, tethered to the tugs by cables that thrummed with strain. The crossing would take 4 days at walking speed, 80 miles of open water, minefields, U-boats, storms, and if a tow cable snapped under load, the recoil could cut a man in half or capsize a tug. The engineers had done everything that mathematics and testing could do. Now the sea would decide whether Churchill's impossible harbor would float or sink, or simply break apart before it reached the beaches of France. The first convoy left Portsmouth at 400 hours on June 7, 1944, less than 24 hours after the initial D-Day landings. 6 tugs, straining against their tow cables, hauled 3 Phoenix caissons into the channel at 4 knots, barely faster than a man could walk. The caissons rode low in the water, their tops 15 feet above the surface, trailing wakes that spread wide and flat in the morning darkness. On the bridge of the lead tug, HMS Assurance, Lieutenant Commander James Walsh watched the tension gauge on the tow cable oscillate between 180 and 220 tons as the Phoenix yawed in the swell. The cable was 2 inches of woven steel rated to 250 tons, and Walsh knew that if it parted under load, the recoil would come back like a whip crack, traveling faster than sound. In 1942, a tow cable failure off Scapa Flow had killed 3 men on a tug's foredeck, the severed cable cutting through a steel rail and a man's torso with equal efficiency. Walsh had seen the wreckage. He kept his crew off the foredeck and his eyes on the gauge. The crossing was a navigator's nightmare. The channel between Portsmouth and the Normandy coast was 80 nautical miles of tidal currents, shifting sandbars and minefields that had been swept but not cleared. German E-boats still operated out of Le Havre, and U-boats transited the western approaches on their way to and from Atlantic patrol stations. Allied fighters maintained air cover during daylight hours, but the caissons were too large to hide and too slow to evade. Every convoy had to follow a precise course through swept channels marked by Dan buoys, staying within the safe corridors while making no more than 5 knots. The Phoenix units, hollow and buoyant, caught wind like sails. In a 15-knot breeze, the lateral pressure could push a caisson a quarter-mile off course in an hour. Tug captains compensated by steering into the wind, but the constant correction wore on engines that were already running at maximum continuous power. Fuel consumption doubled. Engine room crews monitored bearing temperatures and oil pressure, knowing that a breakdown in mid-channel meant cutting the tow loose or being dragged backward by 6,000 tons of drifting concrete. The first caissons reached the Normandy coast on the evening of June 10th, 4 days after leaving England. Royal Navy minesweepers had marked the positions where each Phoenix would be sunk, anchoring Dan buoys in precise coordinates that had been calculated from tide tables, depth soundings, and aerial photographs. The sinking procedure was methodical and irreversible. Compressed air was bled from the ballast chambers. Seawater flooded in through valves in the base. The caisson settled slowly, sinking 6 inches per minute until the bottom touched sand 25 feet below the surface. Engineers in small boats circled the structure, checking alignment with surveying transits, signaling corrections to the tug crews who nudged the Phoenix into final position using low-power engine thrust. When the alignment was confirmed, the remaining ballast chambers were flooded and the caisson sank the final 10 feet, grounding firmly on the seabed. The top remained 15 feet above the waterline, forming a wall of concrete that stretched in a gentle arc parallel to the beach. The first section of breakwater was in place. By June 14th, 70 Phoenix caissons had been positioned off Arromanches for Mulberry B, the British harbor. Another 45 were being sunk off Omaha Beach for Mulberry A, the American installation. The caissons were staggered in overlapping arcs, creating a breakwater nearly 2 miles long at each site. The gaps between individual units were narrow enough that wave energy dissipated before reaching the harbor interior, but wide enough that tidal currents could flow through and prevent scouring behind the wall. Behind the Phoenix line, the block ships were being scuttled. Obsolete freighters and worn-out warships, stripped of guns and machinery, were towed into position and opened to the sea through seacocks and explosive charges. The ships settled in minutes, their superstructures still visible above water, forming a second barrier that broke the smaller waves and chop that penetrated the outer caissons. 70 ships went to the bottom in 3 days. Crews abandoned. Each vessel in lifeboats just before the charges fired, watching their ships die in service one last time. The whale roadways came next, towed across the channel in sections and assembled on site. Each pier consisted of a dozen 80-foot roadway spans mounted on pontoons, linked by flexible joints, and anchored to the seabed by steel piles driven through guides on the pontoons. The pile driving was brutal work. Engineers used diesel hammers mounted on barges, driving 40-foot steel piles through sand and clay until they refused to go deeper. The hammers shook teeth loose and left men deaf for hours. One pile driver worked for 16 hours straight, driving 23 piles in a single shift until the diesel hammer seized from overheating. The engineer in charge, Captain John Richardson of the Royal Engineers, dove into 20 feet of water to inspect the first completed pier at low tide, checking the pontoon guides and pile sleeves for damage. He surfaced and signaled thumbs up. The pier worked. Trucks could drive from the beach to a ship anchored in 30 feet of water, roll aboard, unload, and return without the cargo ever touching a landing craft. On June 16th, 10 days after D-Day, the first Liberty ship SS Charles Carroll nosed into a berth at Mulberry B and tied up to a floating pierhead. Stevedores swarmed aboard, rigging cargo nets and opening hatches. Trucks rolled down the whale roadway, backed up to the ship's side, and took on pallets of ammunition, rations, and medical supplies. The harbor was operational. In the first 24 hours, Mulberry B unloaded 850 tons. Within a week, the figure climbed to 4,000 tons per day. Coasters, tankers, and LSTs queued offshore, waiting for berths. The traffic control was managed from a command post on the beach with signal flags and radio directing ships to specific piers. The system worked exactly as designed. Concrete caissons damped the Atlantic swells. Block ships broke the chop. Floating roadways rose and fell with the 22-foot tide, and trucks rolled on and off continuously, carrying the supplies that kept 7 Allied divisions fighting and advancing inland. And then, on the morning of June 19th, the barometer began to fall. Rapidly. By noon, the wind was gusting to 25 knots from the northeast. By evening, it was blowing 35. Waves that had been 2 feet were now 6 feet, breaking over the Phoenix caissons and surging into the harbor. The storm warning flags went up at 1800 hours. Meteorologists at the Allied Weather Station in Portsmouth reviewed the data and issued a grim forecast. The worst June storm in 40 years was about to hit Normandy, and it would last 3 days. The storm struck with full force on the morning of June 20th. Wind speeds reached 46 miles per hour, gusting to 55, generating 8-foot seas that rolled in from the northwest in waves spaced 70 feet apart. The Phoenix caissons, designed to withstand normal channel weather, began taking hits that exceeded their engineering specifications. Each wave carried thousands of tons of water traveling at 15 miles per hour. When the wave face struck a caisson, the impact generated pressures of 6 tons per square foot, concentrated on joints and seams that had been underwater for only 10 days. Concrete cracked. Steel reinforcement bars bent. Welds opened. At Mulberry A, off Omaha Beach, the first caisson failure occurred at 10:30 hours. A Phoenix Type A unit positioned at the northern end of the breakwater split along a vertical seam. Seawater flooded the interior compartments faster than pumps could evacuate it. The caisson listed 15 degrees, then 20, then rolled completely onto its side, breaking the arc of the breakwater and allowing waves to pour through the gap directly into the harbor. Inside Mulberry A, the floating whale roadways became battering rams. The pontoons, designed to rise and fall vertically on guide piles, were now subjected to lateral forces they were never meant to resist. Waves surging through the broken breakwater pushed the pontoons sideways, bending the piles and snapping the retention pins that held the roadway spans in alignment. One section broke free at 11:45 hours, a 200-foot length of steel roadway weighing 80 tons, driven by wind and current into the side of an anchored LST. The impact tore a 12-foot gash in the LST's hull and smashed the roadway section into 3 pieces. The pieces drifted into other roadway sections, colliding in a chain reaction that destroyed 4 complete pier assemblies in less than 30 minutes. Engineers on the beach watched helplessly as months of fabrication and weeks of assembly disintegrated into wreckage. Commander Joseph Vaghi, the U.S. Navy officer in charge of Mulberry A, sent an urgent radio message to SHAEF headquarters at 1300 hours. Harbor sustained major damage. Unloading operations suspended. Request immediate assessment and repair capability. The reply came back an hour later. Hold position, damage control teams en route, weather forecast unchanged. By the afternoon of June 21st, Mulberry A was dying. 16 Phoenix caissons had cracked or collapsed. The bombardant outer breakwater, designed to flex with wave action, was flexing beyond its structural limits. Anchor chains snapped under cyclic loading. 5 bombardons broke loose and drifted into the inner harbor, colliding with block ships and remaining caissons. One bombardon, weighing 350 tons, was driven ashore by the wind and grounded on the beach like a stranded whale, blocking access to one entire section of the landing area. The whale roadways were a tangle of twisted steel and half-submerged pontoons. Pierheads had been torn from their moorings and capsized. Ships that had been anchored in the harbor dragged their anchors and collided with each other or ran aground. 3 Liberty ships went aground on the beach. And ammunition. Coaster SS Robert Treat broke its anchor chain and drifted into a cluster of beached landing craft, demolishing 5 LCTs before running hard aground itself. By the evening of June 21st, Allied unloading capacity at Omaha Beach had dropped by 90%. Eisenhower's logistics staff calculated that without immediate restoration of harbor capacity, the advance inland would stall within 10 days. Patton's Third Army, scheduled to break out from Normandy in late July, would have no fuel, no ammunition, and no supplies. At Arromanches, Mulberry B was fighting for survival. The British harbor had been built with more redundancy and heavier caissons than the American installation. The Phoenix units at Arromanches were predominantly Type B, the largest and heaviest, displacing over 6,000 tons when ballasted. They were holding, but barely. Captain John Richardson, the Royal Engineer who had supervised the whale installation, stood on the beach at dawn on June 21st and counted 6 caissons showing visible cracks. Waves were breaking completely over the tops of the units, 30 feet above the baseline, sending spray and foam cascading into the harbor. The blockship line behind the caissons was absorbing much of the secondary wave energy, but the ships themselves were taking a beating. 2 freighters had broken their backs, the hulls fracturing amidships and sagging into the water. One destroyer, HMS Durban, had shifted position and was pounding against an adjacent blockship with each wave cycle, opening seams in both hulls. Richardson organized damage control parties and sent engineers into the harbor in small boats to assess the caisson integrity. The work was suicidal. Waves lifted the boats 10 feet and dropped them into troughs, slamming hulls against caisson walls and nearly capsizing the crews. One boat was swamped and 2 engineers were swept overboard. They were pulled from the water by a passing landing craft, hypothermic but alive. The assessment took 6 hours. Richardson compiled the results and radioed them to Admiral Sir Bertram Ramsay, Allied naval commander. 6 caissons cracked but structurally sound, 12 showing minor damage, remainder intact, whale roadways 40% damaged, pierheads secure, harbor operational at reduced capacity. Recommend pumping cracked caissons to maintain buoyancy and welding reinforcement plates over fractures. Ramsay authorized emergency repairs and diverted every available pump and welding team to Arromanches. The storm began to abate on the morning of June 22nd. The wind dropped to 20 knots. The seas moderated to 4 feet. The barometer rose. Across both harbors, engineers emerged from shelters and surveyed the damage in the gray dawn light. At Mulberry A, the devastation was total. 80% of the harbor was destroyed or inoperable. Caissons lay on their sides. Roadways were scrap metal. Pierheads had vanished. Commander Vaghi walked the beach and wrote in his log, "Harbor. Non-functional, recommends salvage of usable components and cessation of repair operations." On June 23rd, Schaeff declared Mulberry a total loss. Salvage crews were ordered to strip anything reusable and transport it to Arromanches. At Mulberry B, the damage was severe but not catastrophic. 6 Phoenix caissons required major repairs. 20 sections of whale roadway needed replacement. 2 pierheads were unusable, but the breakwater had held. The harbor was intact, and on the morning of June 23rd, as the wind dropped to 10 knots and the sun broke through the clouds for the first time in 4 days, a coaster flying the red ensign nosed carefully through the harbor entrance, tied up to a battered but functional pierhead, and began unloading 300 tons of ammunition. Captain Richardson stood on the beach watching the first trucks roll down the repaired whale roadway and allowed himself one moment of exhausted satisfaction. They had built a harbor that the skeptics said could not exist. They had towed it across the channel, and it had survived the worst storm in 40 years. Barely, but survived.